Let us now summarize where we are. To summarize, we want to deal with collections, sets of objects. The underlying motive, of course, is that in chance experiments, we've seen even in simple settings that we deal with aggregates, collections of outcomes, and we need a language to be able to describe these aggregates, these collections, these sets. So this is what we need in our vocabulary. Let's start with the column on the left. First, what are the raw items? We start with a universal set. In the theory of chance, we will shortly call this the sample space. Generically, we'll represent it by an uppercase Greek letter omega. In practical settings, omega will mean different things. For example, a set of graphs, a set of pairs, a set of numbers, a set of functions. Generically, abstractly, it's omega. Elements of omega, and shortly we'll be calling them sample points, are represented by lowercase Greek letters, in this case lowercase omega, and there's an idea of membership. These elements are members of this universal set, and we have a membership notation. Once we have a universal set, we can form subcollections, and these lead to subsets, and now we have notation and terminology for subsets. A is a subcollection or subset of omega. And we have a method of visualizing these subsets and their relationships with each other and the whole, and this is through the medium of Venn diagrams. Now, I should not overstate this or oversell this. Venn diagrams are useful, but they're limited. They're fine when you're dealing with one or two or three sets, but they rapidly become cumbersome when you have more than three or so. Okay. But they're still a useful visual mechanism to capture some ideas of abstraction. Now, once you have this terminology and notation in hand, we go on to the kinds of things we can do with them. So this is the second column. We're talking about a basic set operations. The idea is, how do you construct new sets from old sets in principled ways? The three basic operations are unions, intersections, complements. In logic, ors, ands, and nots. These are the fundamental operations. With these in hand, you can construct more complex operations. Two more that crop up frequently enough to make it worth remembering are set differences, A minus B. Bear in mind that this is not transitive, this is not commutative. A minus B and B minus A are different. And the second, a symmetric difference, A triangle B. The symmetric difference is commutative. Okay? It stands for a cleaned up union, as it were, which eliminates common elements. These are the basic operations by which we construct more complex elements from simple elements. And finally, where do these operations lead us? What kinds of true facts, theorems can I discover? The key discovery is that these operations stand in the role of addition and multiplication. There is an algebra of sets. The empty set stands in the role of an additive zero. The universal set, the sample space, stands in the role of a multiplicative unit. And once you have these in place, we can do unions and intersections freely by understanding, first, that unions and intersections can be done in any order. These operations are commutative and associative. And that furthermore, just as in ordinary arithmetic, unions distribute over intersections and intersections distribute over unions. In other words, we have a distributive property. Together, this describes an algebra of sets. From this understanding, we can derive other deep and interesting properties, and the key one for us is that encapsulated by De Morgan's laws. The complement of a union is an intersection of complements. The complement of an intersection is a union of complements. We conclude by putting together a methodology for verifying equality. If we want to show that a particular identity is true for sets, what we show is that the set on the left is a subset of the set on the right, and simultaneously the subset on the right is a further subset of the thing on the left. Together this will establish equality. Now we should go back and remember A, the notation and the terminology, B, the basic operations. You should be able to write down unions, intersections, complements, set differences, symmetric differences, without having to look at the definition. If you need to go back and look at a definition, then this is a clear sign that you don't really understand the definition. So this should be hardwired into your understanding. And with these in place, you should remember the basic operations, the commutative and associative operations, the distributive operations, and, very importantly, De Morgan's laws. This concludes our little excursus into the theory of sets and set operations. These will establish an alphabet upon which we can build a theory of chance. Our next tableau, then, will go back to the kinds of intuition we built up from our explorations of chance in commonplace settings in Tableau 3, and use this as a springboard to launch us towards the elements of an abstract construction of an axiomatic theory of chance. This was the theory of chance discovered by Andrei Kolmogorov, codified by Andrei Kolmogorov in 1933. So our next step in the next tableau is to build upon this intuition, use the language of sets to deduce what we would want in a theory of chance and put together such an axiomatic theory. Very abstract, I know, but at this point we are building up notation, terminology, a language with which we can talk about interesting and deep applications. We'll follow it up immediately in the following tableau by going back to a humble coin toss.